Hello, and welcome to Physics 2211, Lab 5, Choose Your Own Adventure. For this lab, I chose the falling slinky example. Introduction. The purpose of this lab is to model the motion of a stretched slinky dropped from a static equilibrium. This experiment answers the following questions. How does the slinky move? Does the bottom of the model's slinky stay stationary, just like in the video? And then we create and analyze two different graphs, a computational and observed. The system is the slinky in the earth, and the surroundings are everything else. Some fundamental principles for this lab. Newton's second law, the momentum principle. The net force is equal to the change of momentum over time. We use this to figure out the velocities and the positions, and we continue to input these values in using the velocity update formula, which allows us to predict final velocity during a specified time interval, and the position update, which allows us to predict a final position at a future time. Some more fundamental principles are the gravitational force, where the force of gravity is negative mg times j hat. So the slinky force, or the tension force, is what's applied against gravitation. And there's also drag that changes the speed of the object as it falls through the air, which does not show up in the computational model. So here, the net force is gravitational force, drag force, and the slinky force, all combined. So a brief preview for the first part of this lab, the force of tension will be equal to the force of gravity, causing the bottom of the slinky not to move. However, after a certain amount of time, the bottom of the slinky starts to move due to a greater force of gravity than the force of tension. When compared in a video of the tracker analysis to a computational model, may expect slight differences due to tracker error, and graphs will show constant position for the first half as the bottom does not move, while the second half of the graph will show the position moving downward due to the force of gravity. Here's our observational model. Our real-world demonstration of tension and gravity forces being equal for some period of time. This provides our observational data that can be used in the computational model. The initial condition of the slinky is that it's 0.25 kilograms, and that the delta t is 0.467 seconds. Here are a computational model for the initial conditions. Here's where we input the ball's mass, the initial vectors for position, and all of the constants of proportionality and gravitational. For the first loop, we will use this to find the gravitational force and tension force being equal, causing the bottom of the sling to remain at a certain position. So you see here, that work equals negative ball mass times g j hat, which is equal to the force net. We input it into the update position and update velocity formulas, and then we advance time. The second loop is for when the bottom of the spring starts to move downwards, accounting for the drag force. The delta t is set to be the set time that the bottom starts to move in the observational model. You see here, we calculate for the gravity force, the drag force, and the net force, add those into the update position and update velocity formulas, and advance t. Here are the results. On the left is the tracker. In the middle is experimental versus model, and on the right is the glow script. As here, the glow script has a more equal curve that looks to be more proportional than the real model. So we'll talk about why this might be a little bit different. The reasons why is the tracker analysis might have some user error when tracking the bottom of the sling. The mass of the spring could have been off, or some other sources of error as well. Some similarities and differences about the observational and computational model show the bottom of the spring remain in constant position for a specified time interval. Computational model shows the bottom of the spring moving downward as a straighter, more even slope. Conclusion, what does this mean? The computational model does show that the bottom of the slinky stays stationary for a certain period of time. It is because the computational model shows that the force of gravity and force of tension are equal for a specified time. However, the force of tension eventually becomes less, leading to the downward movement of the bottom slinky, resulting in us having to account for the drag force in the second half of the lab. Thank you.